Good afternoon, this is Schweitzer, and we're going to give the answers to a ionic versus covalent, and this is involving a major topic in advancement chemistry involving bonding of different things, intermolecular forces. Pretty big topic. Alright, so first things first, K2O and K calcium oxide are two metal oxides that are very insoluble in water. Alright, how might the melting points compare between two salts? I'm not sure at this point why that's there, but they're strong bonds. Okay. Either way, so when answering this question, I would often like to say, how are the melting points compare between the two salts? Justify using Coulomb's law. So Coulomb's law is the force of attraction is equal to the charge of the cation, charge of the anion divided by the distance squared. So in this case, the first thing we go to is these charges. This one here is a plus 1 minus 2 plus 2 minus 2. And at that point, you say, well, due to the larger difference of charge, calcium oxide has a larger charges and therefore has increased Coulomb attraction and therefore has a higher melting point. Next one, how might the melting point of Na2O compare to the relative to the previous two? Alright, so we have K2O is here, and we have CaO is here. This guy is plus 1 minus 2, plus 2 minus 2, okay. So we have Na2O. This guy is a plus 1 minus 2. Okay, so it's going to be very close to this one. Question is, which side does it go on, that side or that side, as far as lower or higher melting point? Well, what you do is go to a periodic table and say, what is the internuclear distances like? Okay, looks like potassium is bigger than sodium. Alright, so that means the internuclear distances of the potassiums and the oxygens is larger than this guy. So this guy is smaller, so the atoms are closer together. Again, the distance is smaller, creating a larger Coulomb attraction, making Na2O our next highest. And that's the order in which they're at. You'd be right between the two. And that order is listed above here, lowest to highest. Below are two models attempting to show the bonding of calcium oxide. Alright, they both show 1-to-1 ratios, but this little line right there means that we're covalently bonding, means we're sharing electrons. In this case, that is not what we want. This is an ionic compound which forms a bulk crystal. Cations anion, cation anion, blah blah blah. Okay, so the second one is the best option here. Which of the symbols is calcium? Okay, so again, how many energy levels do we have? Let's find these things on the periodic table. Calcium's here, oxygen is way over here. Only has 2 energy levels here versus calcium has 4. Well, it's calcium ion, so either way, it's got more. So in this situation, the big one is the calcium atom. The big one is the calcium atom. Small one is the oxygen. And what do we do here? All right, so things appear to be good. All right, next up, so the big one's calcium, small one's oxygen. Other than the term ionic, what word might describe the force holding together this substance? Coulombic. All right, next, sodium nitrate. This substance is both ionic and covalent. Justify or nullify. Justify that thing. Okay, right here, there is an ionic compound. That's the cation, this is the anion. This anion happens to be a molecule of nitrate, which is held together by covalent bonds. you can draw a Lewis structure of this guy. And you'd have a little something like this with little dashes showing shared electrons. So both are present. All right. When dissolving, both ionic and covalent bonds are breaking. Justify or nullify this. When I dissolve this thing, I want to be able to show here that, okay, it's solvation, so the nitrate would go over here, and the sodium would be over here, holding around this guy. We call this an ion dipole. And what did we break there? We actually only broke ionic bonds. The covalent bond did not break. Draw the molecule, show how it dissolves. We did that already. Label the location and the type of bond. Now, this is not a very common question. So be careful how you draw that thing. It's located right there. It's called the ion dipole. But be very careful you don't show a solid dash. And I wouldn't be one to show any of this unless it specifically asked me to do that. I'm using dots to show just that type of attraction there, an intermolecular attraction, not nearly as strong as a covalent bond. All right, next one. All right, I2 or elemental iodine is solid room temperature, but when heated, it vaporizes. Okay, substance is covalent, justify or nullify. That's a justify. All nonmetals is covalent. When vaporized, covalent bonds are broken, justify or nullify. That's a nullify. We would have solid iodine vapor, and when you vaporize it into vapor, the vapor also would be iodine molecules. So when you vaporize it, you're not breaking the covalent bond. You're breaking the intermolecular attractions between these guys. And that particular attraction, even though it doesn't say it here, you should be aware, is simply London dispersion forces. And it doesn't take much to break those, so the heat of vaporization is not that much. All right, create Lewis structures for all of these substances. Okay, so this is a skill that people tend to get rusty on. So in this situation, I'm going to go through a couple of them. Maybe all of them, we'll see. So xenon has 8 valence electrons, chlorine has 7, and there's 2 of them. People want to go too fast with this. Just take your time, and this is how it works. So 7 times 2 is 14. 14 plus 8 equals 22. So we have 22 electrons in this thing. Now again, we don't have to have it to be even, but if it's odd, it's called a radical, not very common. All right, so we have xenon, and we have chlorine, and we have chlorine. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2 left over, put them on the center. This central atom has 1, 2, 3, 4, 5 domains. I'll take all those circles off there, that's the Lewis structure. Electronic shape, 5 domains, is trigonal, bipyramidal. Now the molecular shape is just the xenon with a chlorine and a chlorine. This one actually, I lost all 3 off the middle here. Its shape is just linear. Hybridization, S, P, 3, D. 3, 4, 5. 5 things off the center. Ammonia. Okay. Nitrogen, it's got 5 valence electrons. 1 times 3. And we are in a total of 8 electrons. Must follow the octet rule, by the way, because it's in the second row of the periodic table. Nitrogen, hydrogen, hydrogen, and hydrogen. 2, 4, 6, 8. Done. This guy's electronic shape is tetrahedral. Molecular shape. This one here will not show up in the picture. It's called trigonal right? Pyramidal. These angles here, because you got 4 things off the center, is real close to 109. All right, 109. Pretty common question there too, I guess. Justification. SP3. All right, this guy. One more than that guy, so it's well, it's got 5 plus 4 lost an electron. Take one away. We're down to 8 once again. All right, so we have nitrogen in the center, hydrogen, 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 and that's 2, 4, 6, 8. Done. Hydrogens can only bond one time. Bracket with a positive charge. These two are the same because there is no unbonded pairs. It's tetrahedral for both. 4 things off the center. All right, carbonate. Carbon is going to have 4. Oxygen is 3 times, well, it's got 6 valence electrons, and there's 3 of them for 18. 18 plus 2 is 22. Add 2 more on, 24 electrons. All right, carbon, double bond oxygen. Oh, I'm getting ahead of myself here a little bit. All right. Doesn't want to do that. Okay, so carbon, oxygen, oxygen, oxygen. 2, 4, 6. I fill the center one first so I can share in any direction. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Shorter pair. Take a pair off a neighbor. That's why I like to fill that one first. And share between. I have a bracket here with a negative 2 charge. Because you could equally be drawn the other places, this will resonate, and I want 3 more drawings, 2 more drawings. One of it double bond top, 1 double bond. 3 resonant drawings total. All right, three things off the center. So this is trigonal planar. All domains are bonded, so these are the same. The angles on this guy are about 120 because there's just 3 things off the center. This guy here is still SP3, and that's 4 things off the center. This is going to be SP2. All right. A few things about this one. Okay, 6 things off the center. Again, for me, that's about maximum you can get. This is 6. This is 6 times 7. Right, that's 42 plus 6 more is 48 electrons. Sulfur goes in the center. You have fluorine, 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 fluorine. Now, I had kids in the past that get so used to just sketching these out, they forget to put the dots on. So don't forget, all of these guys will get the full allotment electrons, and you cut them up, you will see that we will get to 48. Shape. Now these are again both the same because we don't have any unbonded pairs. Octahedral. SP3D2. All right, PF5. All right, this guy's going to give me for phosphorus. All right, right under here, right, phosphorus. 5 valence electrons. All right, so we're going to get 5, and then we got phosphorus is going to be 5 of them, and 7 is 35 plus 5 is 40. 40 electrons. Set up our skeleton structure. Phosphorus, chlorine, it's fluorine. Do it. There it goes. Thank you. Phosphorus to fluorine to fluorine to fluorine to fluorine. So I have right now I got 5 domains off the center, but I don't know about unbonded ones yet. So 40 electrons is where I'm at. To count the middle ones, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Done. No extras to put in the center. That center atom will need to be in the third row or bigger to handle the extra electrons, but we don't need them. So 5 things out of the center, no unbonded pairs, these are the same. That's 5 things out of the center is trigonal bipyramidal. And sp3d. All right, H3O plus. Right, hydrogen 1 times 3 is 3. Oxygen is 6. That's 9. Lost 1 for 8. All right, oxygen goes in the center. We got hydrogen, hydrogen, and hydrogen. 2, 4, 6, 8. And we're done. In this case, I have a bracket with a positive 1 charge. 4 domains off the center, so that's tetrahedral for all my domains. This is going to be trigonal pyramidal, and therefore sp3. All right, next one. The acetate ion structure is listed below. Draw the resonance structure. Okay, so it's going to be H, carbon, hydrogens, carbon, single bond oxygen, double bond oxygen there, and of course we make sure we have all the electrons on here, and bracket with a -1 charge. All right, load of work. You should try those, and hopefully try them and you're getting the rust knocked off of those. For each carbon center, list the hybridization for the last guy. Okay, so let's see what we got here. List hybridization, each carbon center. All right. Now that guy there has 4 domains. That's tetrahedral. Let's just say it wanted the hybridization. 4 things of center, that's sp3 tetrahedral. 109 degrees, all these guys. But these angles, even though they're look like they're different, they're actually all the same. 3 things off the center, that's sp2 120 degrees and trigonal planar. So what else it says? How do the carbon-oxygen bonds and the carbon-oxygen bonds compare in length? All right, so in this case, you should note they're the same atoms. We should note the double bond is simply going to be shorter. Okay. Now, in that situation, we know double bonds are shorter, but in this situation, we do have a resonance structure. So a straight double bond would be shortest. A straight oxygen, single bond we double, but this actually got a bond order of 1.5. So even though it's shorter, that's the answer to the question. It's resonating between 2 different places, which actually makes it like a bond and a half, which would be between those 2. So a straight double bond would be shorter than this one. This is acetic acid, acetate, so a hydrogen would like to go on here. That makes it back to vinegar. That removes the resonating factor, which then makes this thing shorter. All right. Intermolecular forces. Water is a substance known for containing hydrogen bonding. Okay. Draw 2 water molecules and label this intermolecular forces. Pretty common AP problem. So they're going to just give you the drawing. And I may do it like that. Careful about how you draw that, just dot-wise. This is my hydrogen bond. And then this is my covalent bond. This is this is the inside bond inside the molecule. Therefore, that would be the intra. And this right here is the inter. All right. What characteristics of water give it the ability to hydrogen bond? All right. Well, first of all, it's polar. So how does it become polar? Well, we have a highly electronegative atom, which would be oxygen, and it's sharing electrons to a hydrogen. Electrons are then dragged over to the oxygen for a partial negative, partial positive. So, in this case, it's polar with a hook to a hydrogen. Student hypothesis, carbon dioxide is a highly electronegative atom, therefore it will be polar. It does not have a hydrogen. So it will be having dipole-dipole interactions with carbon dioxide molecules. Just to nullify all aspects of this reaction. And in this case, the answer would actually be nullify. Some of it there is true, but the problem with this one is that it is symmetrical. And that causes cancellation of the dipole, and therefore it does not have a dipole and is not polar. And therefore, we can automatically get rid of the dipole-dipole, and of course, no hydrogen bonding. Iodine is a solid and fluorine is a gas at room temperature because iodine is more massive. Just very nullify. Well, in this one, I might call the bluff on this one. Nullify. It's not a solid because it's more massive. It's solid because it has more electrons. Therefore, increase London dispersion forces. Now, I don't believe that this is something they would put on an AP test. What they would do, however, is that when you justified it, and if you put more massive, then they're going to mark it wrong. But they're not going to put more massive on there because it's too close. But make sure you reference more electrons, not just simply more massive. List factors that might cause a substance to have greater London dispersion forces. More electrons. And of course, longer chains. Justify or nullify the following questions relative to magnesium nitrate. Magnesium and nitrogen are sharing two pairs of electrons. All right, first of all, this is a metal and not in a polyatomic anion. We're not sharing any electrons. We transfer electrons forming ions. So the answer is nullify, and we're not sharing anything. The substance is heated to a very high temperature, breaking into magnesium, nitrogen, and oxygen atoms. The bonds that are broken in this process are ionic. Well, that technically would be nullify. So in this situation, we have two different types of bonds here. I even just told you it's ionic, but now I'm telling you I'm nullifying that. Okay, well, we have a magnesium ion, and it is ionically attracting to a nitrate, NO3 minus. But if we heat the daylights out of this thing, and we break this bond, and we break up all of those bonds, inside there is a covalent bond. And therefore, technically, it's nullified because we have broken both ionic and covalent. When this substance is dissolved, it can be modeled as followed. Okay. So, justify or nullify this. Once again, I will nullify. When this thing dissolves, the nitrate will stay together, it will not break apart. So it would be magnesium 2 plus plus NO3 minus. course, that balancing would be a 2 there. The magnesium nitrate can only conduct electricity when dissolved in water. Otherwise, it's a non-conductor as a solid. This is true. You need free moving electrons, ions, or charges to get this to happen. And in a solid, those charges are locked in a crystal and cannot move. Therefore, a solid rock of magnesium nitrate is non-conductor. When diamond is melted at over about 4,000 degrees, why such a temperature is needed? Well, the stronger the bond, the more energy needed to break it. Stronger bond is being broken. And that bond that's being broken is covalent. An ice cube is placed in your hand. The warmth of your hand causes it to melt. Does the ice get colder, warmer, or stay the same as the ice melts? The answer is it stays the same. Not quite sure what this has to do with bonding, but it's more of an energy question and states of matter question. So we're going on our heating curve here. You should note the temperature is located here and right here. Your hand gets colder. The ice stays the same. We're just flipping phase. So we can have 0 degrees ice, 0 degrees water. Notice it says as it melts. So technically same temperature. All right. All right. All right, now we're going on B now. So it's the same problem. So we're melting ice, H2O solid going to and from H2O liquid. It says no London dispersion forces are broken or disrupted in this process, just or nullified. Now, we just mentioned that this thing is being held together by hydrogen bonding. Now, this is one thing we got to be careful of. Everything has London dispersion forces. So the answer is true. Because everything has this. And they will catch people on this. This is one thing that they will catch people on. Everything has London dispersion forces. Even ionic compounds have London dispersion forces. They're just smaller compared to everything else that's there. Dichloromethyls, CH-DCM, common liquid solvent used for extraction of caffeine from coffee and tea. The following reaction is used to make DCM. Makes a variety of products, which then separates them via distillation. Okay, so we make this reaction, we make all of these things. Okay. Draw a Lewis structure of DCM. That's dichloromethane. That would be this one. So carbon, carbon. Carbon bonds 4 times. You can add up all your valences. That's fine. But you should note that you can do it just like this. Of course, you cannot leave it like this. You have to add in your electrons to get to octet. And again, verify. I guess you'd have to have that. All right, dichloromethane. Someone else, and you can actually let's do this thing a different way. So I think there might be a mistake there. So carbon is dichloromethane. So C2H2Cl. All right, so I got 2 times 4 is 8. 2 times 1 is 2. Dichloromethane. So 2 times 7 is 14. 14 plus 10 is 24. So let's set it up. Carbon, carbon, hydrogen, hydrogen, chlorine, chlorine. 2, 4, 6, 8, 10. All right, 12, 14, 16, 18, 20, 22, 24. I'm short 1 pair here. I didn't have an opportunity to put it on. I ran out of electrons. Take a pair off and share between. And this is the right answer, not that one. All right. All these substances are liquid. What force is producing this effect? All right. Now, whenever I see, well, first of all, they're all molecules. Okay. Whenever I see molecules, so I'm already crossed out the fact that their ionic is out. Network covalent is out. All I have left is covalent molecular substances. So the first thing I'll say, okay, do I have a highly electronegative atom to create a dipole? The answer is no. If I don't have any of these, then my next, so that kind of removes hydrogen bonding and dipole. Now, just a clarification point, really important for overall understanding. I always talk about these as being required, but if I didn't have one of these and I had some other, like chlorine, for example, chlorine's still going to cause some amount of dipole moment. Now, it might not be as much. We might not call it a polar molecule, but it's going to have some polar characteristics, not like the switch goes on and off with these guys. Symmetry, however, can shut off entirely. So that is always something that you want to discuss if it's a factor. It's nonpolar because it's symmetrical. That's more important than maybe not having one of these. All right. Now, again, none of these guys have highly electronegative atoms. Some of them are symmetrical, some are not. So do they all have the same dipole moment? The answer is no. This one's completely symmetrical. So this is a dipole moment of 0. But these ones are not. This one and this one and this one are all asymmetrical and therefore would have some amount of dipole characteristics. They might not hydrogen bond, but they could have a small amount of dipole-dipole, which would cause a slight variation in melting points. Important. And it would appear that is all. Thank you.